let's get going with exponents today. An exponent is often thought of as sometimes called a power, or we often say raised to. And the idea is that if something is squared, like if I have x squared, that's the same thing as x times x. So whatever the base is, it gets multiplied by itself that many times, given whatever the exponent is. That's sort of the default way to think about it. Where it gets a little more confusing, or at least more sophisticated, is when an exponent is negative or when an exponent is a fraction. Okay, so let's get it going here. When we do exponents, the product rule for exponents, I often like to call this equal bases add exponents when we multiply. So it's called the product rule, but notice if you have the same base but different exponents, we're going to add them. So like for instance, if we have m times m to the 7th times m to the 6th, how many m's are there? Let's do the same sort of thing with this next one. First of all, can we keep the coefficients separate than the x's and the y's? Like multiply those first? Yeah, absolutely. So we could do 4 times -5, make it -20. And then what about x times x? So x squared and then y. And by the way, we want to keep x before y. So whenever possible, even though you could do y x squared, we keep things alphabetical. It's just more organized. Same idea here. Let's multiply the coefficients. What's -6 times -3?
That's just going to be 18, and then a to the power of 3, and then b to the power of 6.
Exactly. Now the thing is, 5 to the power 8 is going to be a very big number, right? We see that it ends up becoming 390,625. Even when you have a number, sometimes it's a good idea to just leave it in exponent form because the number is so large otherwise. Yeah, that's perfect. X power 7. And then what about the last one?
What I do is do x and then y squared, or does the order matter?
So it does to keep things organized. Like I said, technically it's still the same answer, but I would highly recommend we always put x before y because it's alphabetical. Say you had like a term like 5x squared y. You'd put that first because the power on the x is larger than this term. Whenever we have multiple terms of the same variable, same base, we have the powers going down in descending order from largest to smallest. But then when we have multiple terms, like multiple bases, we always go alphabetical, x and then y. Yeah, so power 0 is a very special power. Now, by the way, it's actually best to understand this rule from the rule below. So let's take a look at the rule below. The rule below is called the quotient rule, but in a very similar way here. Remember we said equal bases add exponents when we multiply? The quotient rule, you could say equal bases subtract exponents when we divide, right? It's just the other way around. So, right, 3 to the power 2 is 4 minus 2. This is going to be y to the power 4, perfect. And then what's 20 divided by 4? Is 5, and then x squared. Beautiful, perfect. Now, here's an interesting question though. Suppose I had x to the 7th over x to the 7th. So first of all, I get x to what power via subtraction? Right, x to the 0. That's exactly right, because that just follows the quotient rule. But then here's another question. X to the 7th over x to the 7th is like the same number over itself. So that's like the number 17 over the number 17. But that always gives us what special number? Anytime you have any number or any variable raised to the 0 power, it always gives you 1. Because the way to think about it is, it's whatever power you want to think of over itself, and they would just cancel, so you get 1. That's why this power 0 rule exists. Do 12 and 14 share a greatest common factor?
It's gonna be, I guess, 2?
Yeah, 2 is the greatest common factor. So divide 12 by 2, you get what number? Yep, 6, and then divide 14 by 2. Okay, so it's going to be 6 over 7 in terms of the coefficients first. Now, in terms of the y's, we're going to get y to the 10th over y to the 8th. That's subtraction, so we get y to the what power?
Y to the power of 2.
That's right. So you can say squared, power 2, second power, so all the same. And then lastly, we've got z to the 7th over z to the 7th. Well, 7 minus 7 is what?
That's just gonna be z to the 0, which is just 1.
Do we even need to include it? If you multiply something by 1, is it just itself? So that should be our final answer. 6y squared over 7. So the thing is, the 14 was downstairs. It did not divide out completely, so it remains in the denominator in the final answer. All right, now this is when things get a little more tricky. One way to think about y squared over y to the 4th is to think about y times y over y times y times y times y. Because that's what it means, right? Just there's 2 y's upstairs being multiplied, and there's 4 y's downstairs being multiplied. So how many of them cancel out? So 2 minus 4 is negative 2. But do you also notice after canceling those out, we get 1 over y squared, because there's just 2 y's downstairs. But wait a minute. If you just use the same rule that we did before, the subtracting exponents rule, the so-called quotient rule, that's the same thing as y to the negative 2. So y to the negative 2 is the same thing as 1 over y squared. So that leads us to this really interesting formula. And the formula says that any base to a negative power is just 1 over that same base to the power, but then take off the negative from the exponent. It works the other way around. So if you have 1 over b to the negative n, that's just b to the n. Because if you got a negative exponent downstairs, it flips it to the top. Whereas a negative exponent upstairs flips it to the bottom. The negative exponent is kind of like a reciprocal flip, if you will. Now, by the way, be careful. We're only going to flip the things that have negative exponents. So like, for instance, on the first example, we're going to have 7x over y to the 4th. Because when you flip it to the bottom, it becomes a positive exponent in the denominator. Because just think about this minus 4 right here is just like how this negative m acted right there. When you flip it to the bottom, it becomes positive on the bottom. The next example is a nice example because it uses both rules. So I'm going to suggest the x to the minus 7 gets flipped to the what? 1 over x to the 7. Then the other one down here is going to give us y to the 3rd over 1. Flipping it to the top.
So why is the y like up, but the x is like down?
Yeah, good question. So remember, when you have a negative exponent, if something is living in the numerator, it flips to the denominator. If it's living in the denominator, it flips to the numerator. What that means is, in the final analysis for this problem, it's just going to resolve itself to y to the 3rd over x to the 7th. Because it's just y to the 3rd got flipped up, and then x to the 7th got flipped down. Now for the next problem, one of the things we note is that, of course, with these exponent rules can be combined. So p to the minus 3 can get flipped up to the top. You have 5p to the 4th power times p to the 3rd power. Can we now use the exponent rule back here where you have equal bases add exponents when you multiply them? And then you just get 5p to the 7th. How about the one on the bottom there? So that one's got quite a few things going on. So I'm going to recommend that we can combine things before we work with it. Upstairs, can we add exponents because we have the same base? So the power is x to the 7t minus 1 over x to the t. Now, because they're divided, can we go ahead and subtract powers? So it's going to be x to the 6t minus 1, and that'd be your final answer. What you could do is you could do this. Do you see that here we're usually adding powers? It is possible to reverse it by, you could separate the 6t and the minus 1. So you can make this x to the 6t times x to the negative 1. But if you did that, notice that would just be x to the 6t over x, because the x to the negative 1 just drops to the bottom. Both of those answers are fine answers. It's just that it depends upon what form they want it in. It does say up here on the instructions, positive exponents only. So probably this one over here on the right is probably what they're actually going for. Let's see, the last one. Can we change spots first? Like, in other words, can I send the negative 7th power to the top? So at least in terms of the 11s, this is what we have so far. What can I do with the b to the minus 4? So we got b to the 3rd and then b to the 4th. Got that so far? So let's go 7 minus 9 in terms of the powers in the 11. That's going to give you 11 to the minus 2. But then we're going to end up with b to the what power? B to the 7th. Next thing, can we send now the 11 back down to the bottom because it has a negative power? Now, 11 to the power of positive 2, that's relatively easy to do. It's not a big number. It's just 11 times 11. It's 121. So the final answer should be b to the 7th over 121, and then done. So some more exponent rules include, what if you have power of a power? So if you have a power raised to a power, then you multiply powers. So that's going to be multiplying powers. That's going to be z to the 15th. And then you can also have a power over a product, distribute the power over the product, or a power over a quotient, like a division, you can distribute the power over the quotient. And then the other rules we already kind of covered. So you got z to the 15th for the first one. That's good. How about for the second answer? What are you going to get? 3 to the what? Okay, so let's start off with 3 to the negative 12 power, but then that ends up becoming 1 over 3 to the power of 12. So it's 1 over 531,441. So some teachers are very strict that they want you to finish the full calculation. Some teachers are okay with this. So this is okay, and then this right here, of course, is totally finished. Let's go for the next one, the one with x. Yeah, just x to the 24th. That's actually pretty easy. X to the 24th. Now let's go for the next problem. So first of all, should we end up with x to the power 6 when we do power of a power? It still ends up being 5 to the 3rd. So you still treat it like traditional. 5 to the 3rd is 5 times 5 times 5. And then this ends up being x to power what, like you were saying? Yes, because it's 2 times 3. Bringing the power into the inside. And when you bring it to the 5, it's a number, so it's 5 raised to the power of 3, and that's just a calculation. 5 times 5 times 5. Given it's x squared to the power of 3, that's like x squared times x squared times x squared. But x squared times x squared times x squared just ends up being x to the power 6. You could just multiply them. So it's going to be 125x raised to the 6th for the final answer. Next, we've got this large product all raised to the 7th. So once again, should we use power of a power and multiply the powers for all the terms? Yeah, so it's going to be x to the what power starting off?
X to the power of, negative 35. Y to the power of 14. And then the last one is going to be z to the power of negative 7.
Gorgeous. Exactly right. Remember, in the final analysis here, we only want positive powers. So what should we do with the x to the negative 35 and the z to the negative 7? Yeah, make it a fraction. Exactly. Let's see. We've got 2 to the negative 2 over y, and the whole thing is raised to the negative 2. Again, can we still bring the power into both the terms? So that's going to be 2 to the power 4. Perfect. 2 to the 4 is like 2 times 2 times 2 times 2. But then, because y is the negative 2 power, we should flip it where? And that's your answer. See how that simplifies really nicely? An alternative way you could have simplified this using the other rules is because the entire thing has a negative right here. You could have made this y over 2 to the negative 2 squared. Do you see that? I took the negative on the outside, I just flipped them both. And then you end up with y squared over 2 to the negative 4 power. But that would still give you y squared. And then when you flip the 2 to the negative 4 power to the top, you end up with 2 to the 4th on the top, and that's 16. It turns out you can use these rules, but the order that you apply them is sort of up to you as long as you're doing it correctly. And so we've got 3ab to the negative 5, so it's going to be 3 to the negative 3, a to the negative 3. Now, what do we need to do with the negative powers? And then I think we just have one last step. 3 to the power of 3 is not that hard to calculate, because that's 3 times 3 is 9, 9 times 3, 27. So that's our answer here. And then how about for this last one? Okay, so we got a lot of negative powers going on. Should we be changing positions? So it should be 9 squared. And then let's move the a to the -4 to the bottom. So that should be a to the what?
A to the 4th and a to the 2. And then it's just going to be b to the 5. On the top, it's just going to be b to the 8th. 81, 9 times.
Right, 9 squared is 81.
And then it's going to be a to the 6th.
That's it. Yeah. Nicely done. That's correct.